This is lecture 10 about the chain rule and implicit differentiation for functions of more than one variable. This is covered in section 14.5 in our textbook. First of all, let's recall when we had a function of one variable, y is equal to function of x, and where x is defined by another independent variable t, say, if I have x as a function of t, let's call this function g of t. If f and g are differentiable functions, then I can do the derivative of the function y with respect to t. And if I want the derivative of y with respect to the independent variable t, then we did apply the chain rule to do this derivative. Okay, we said that dy by dt, where y is a function of x, is equal to the derivative of y with respect to x, correct, times the derivative of x with respect to t, since x is a function of t. So this actually means if y is differentiable functions, then dy by dx is the function, the derivative of the function f prime of x, and x is a function of t. So dx by dt would be the function g prime, it would be the derivative g prime of t, right? So this actually is the chain rule when we had a one variable. If I want to draw a tree diagram, then this would be useful in more than one variable. For the idea of this chain rule, actually, we begin with the node where y is a function of x. Then this node have only one branch coming out, in which it is the variable x, where x is a function of t. Then I end up with the independent variable t, where the last node in my tree usually is the independent t, is the independent variable. So when I apply the derivative from the branch from node to node, from here to here, actually this is y as a function of x. So here we have f prime of x, or we call it dy by dx, right? From this node to x to the other node t, I have dx by dt. So overall, when I go from the above node to the ending node, this actually is the derivative that of concern, which is dy by dt. So when I'm the same branch, I call this is a branch, but when I this on the same branch, then dy by dt is equal to dy by dx times dx by dt. I do the product of the two terms and on the same branch. I do product, okay? Let's see about when we have functions of several variables, how we are going to deal with the chain rule. Actually, we have several cases here because we can have several function definitions. So if I started with a function z as a function of x and y, okay, as we see here from this case, and x itself is a function of the independent variable t, the function g of t, and y is the function h, is a function of t and h of t, where f, g, h are differentiable. I know from my differentials before, but I have defined the differentials, okay, of a function of two variables, dz, and I said that the dz, if z is a function of x and y, actually it is partial z partial x times the total derivative dx plus partial z partial y times the total derivative dy. Okay, we had this from last lecture. Now, if I required to find the derivative of the change of the function z with respect to t, I need to find the change. Okay, the change of the function z or the variable z with respect to the independent variable t. Actually, I'm looking for the derivative dz by dt. Okay, if I started from this differential and applied the change with respect to t for overall the whole equation, I'll end up with partial z partial x. So dx will change with respect to t, dx by dt plus partial z partial y d times dy by dt. Okay, so now I have this formula for the derivative of z with respect to t. When I go back to my functions and I said that I have a function x is a function g of t and y is g of t, if I want to go back with these derivatives to the relevant functions so partial z partial x actually is my partial derivative for f sub x of the function x and y, okay? Partial z partial x is this partial derivative fx dx by dt. Actually, this is a function g of t, so this is a function of one variable, so it's a g prime of t plus partial z partial y. Also, z is a function of two variables, so this is the partial derivative fy of the function x of the variables x, y, and dy by dt. Y is the function h of t, so it will be h prime of t. Okay, so I have this formula, and I call this is the chain rule for this case. Okay, this is the chain rule for a function z of two variables, where each one of these variables is a function of one independent variable. If I want to do the tree diagram of this rule value, I have two branches coming out, one for each variable. I have here the variable x and the variable a, y. If I go from each of these nodes, each one of these nodes is a function of t, so I'll end up with the t, and they will combine here at the same variable t, okay? Now let's do the derivatives. If from node to node, actually from w to x, I have partial w, partial a, partial x. From node w to node y, I have partial w, partial y. From node x to node t, you have dx, total derivative, dx by dt, and there is only one branch coming out from x, so it's a total derivative dx by dt. From the node y, هنا هتلاقي برضه dy by dt. We'll find dy by dt. Okay. If I want overall to go from the first node w to the ending node, which is the t, actually I'll call it the derivative w. Now is it partial or a total derivative? I'm ending up with only one single independent variable, so it is a total derivative. In the end, w is a function of one independent variable, which is t. So it's a total derivative dw by dt. Okay, so our chain rule of dw by dt has two branches. This is the first branch, dw by dx by dt. This is the first branch. On the left, dw by partial w partial x times dx by dt. And the second branch will be, but this is the first branch, this is the second branch. The second branch is partial w partial y times dy by dt. So what do I do with both branches? Actually, I add them up. If I'm on the same branch, I do product of the terms or derivatives. If I change from branch to branch, I do addition. Okay, so this is the rule for the chain rule. Why am I concerned about the tree diagram? Because if the cases could change, yani, as we're going to see from the following cases. Yeah. Now, if I have a function of two variables x and y, but this time each one of these independent variable is a function of two. If each one of these variables x and y is a function of two independent variables s and t, as we see here from this figure. The first function x is a g of s of t, and y is a function h of s and t. Now let's do the chain rule. Okay, we're gonna think about it. Is how about we're gonna say actually this is z. Eventually, it will be function of two independent variables. But I could come up from these composite functions with two partial derivatives, partial z partial s and partial z partial t. Why did I say partial, not total? And in the end, I'll end up with two independent variables. It will be clear now from the tree diagram in a while. But let's analogous to the previous case. Let's do it كده. We're gonna say, if I'm gonna do the derivative z with respect to x, and I know z is a function of x and y, then I'll first do the derivative of z with respect to x, right? Times the derivative of x with respect to x. All of these are partial, and each f is a function of two variables, and g is a function of two variables, plus y plus, because I have still another variable y. If I'm going to add up the derivative z with respect to y times the derivative of y with respect to s. Now I have two branches, and two terms, equivalent two terms, okay? And similarly, partial z, partial t, when I go same, maybe I'll go partial z is a function of x and y, but I'll start with the x, and where x actually is a function of this t, if I'm gonna put t plus partial z partial y times the derivative y with respect to t, okay? When we see this in the tree diagram, I will expect that I have two branches for each derivative. If, eventually, when I look at the nodes now, I started with the z node, and I have two branches coming out, one for the x and one for the y variable. If I have these two nodes coming out, and each one of these nodes actually will have two branches coming out. And each one of them is a function of two variables. If I'll have this node and for s and the node for s and t. Actually, there is an alternative way to draw this diagram. I could start with like the previous z. I have these two branches coming out. This is for the x and y, and x will have two branches, which is the s and the t, and actually the y also will have two branches s. I could combine the same s's, and it's the same variable, and the a and the t. If I could, this is an alternative way to draw the tree diagram of this case, okay? So now let's do the branches. بالتالي from here to here, I have this branch, the derivative, I will be actually partial z, partial x. From x to s, I'll have partial x, partial s. Why partial? Tiny, because x has two branches coming out, has two variables, a function of two variables. Similarly, s, I could arrive at this node s from another branch. I could arrive at this s from partial z, partial y, and from z to y, in addition to partial y, partial s. If I tell this is the first branch in which I find the partial derivative, partial z, partial s. Let's rewrite it again from the tree. If you move on the same branch, this is the first branch, or the product partial z partial x, the product of the terms along each branch, times partial x partial s, plus I'm gonna move on to another branch, this one. I will have partial z partial y times partial y partial s, okay? Similarly, I could do it for the other independent variable t. How many branches? Also two branches. I could go like this, partial z partial x, partial x partial t, plus partial a partial z partial y partial t. This is the second branch, okay? Even now I could write the second form, partial z partial t, the second independent variable. This will give me partial z partial x partial t times طبعا هنا في plus partial z partial y times partial y partial t. Okay, general chain rule بقى. Now we saw from the cases that actually we could have other cases definitely, and yes, we could have any general case in which u is a differentiable function of n variables x1 to n to xn, and each one of these x's actually is a differentiable function of m variables t1 to tm. Yani if we write it like this, u is a function of x1, x2, up to xn, you have n variables, and the x themselves, let's call them xi's, are functions of, as in the formula it's xj, is actually the function of other m variables, let's call them t's, okay? If I have t1, t2, up to tm, if I have m of such variables. When I want to draw the tree diagram of this case, actually, I'm going to start with the first dependent variable, which is the u. I have how many branches coming from u? U is a function of n variables. If I have n branches coming from here, if I have the variables along x1, x2, right, x3, up to xn. Each one of these x's is a variable of m variables. From each one of these nodes, I'll end up with m branches. These branches defines the independent variables t1, t2, up to tm. Okay. Similarly, x2 will have m branches from t1 up to 2m. نفس الكلام these xn وبرضه will have a from t1 t2 up to tm. Okay, this is the general tree diagram for any case. Okay, so when I do partial derivatives, if I want the derivative with respect, say مثلا to t1 actually occurs in each one of these branches. But actually my function, our final function, will have n terms. يبقى بالتالي partial u partial t1 actually will be equal to, I'm going to move from along each branch like this, but this will be partial u partial x1 times partial x1 times partial t1. The second branch will u بالنسبة ل x2 then x2 with respect to t1 and so on. يبقى partial u partial x1 times partial x1 with respect to t1 plus partial u with respect to the x2 times partial x2 with respect to t1. I'm ending up with t1 always. Up to to the last term, the nth term, يبقى partial u partial xn times xn with respect to the t1. Okay, يبقى now I have n terms because I started with n variables within the function a u. Okay, this we call it the width and depth of the depth of the tree diagram. I could have further depth, at the T نفسها also could be functions of other values. I don't care as long as I know the concept of the tree chain rule. Now let's do by examples. The first example, Hannah, first of all, I need to observe the number of derivatives, the number of independent variables in the function. Now, z is a function of x and y. So I know that I have a function z of two variables x and y. And now I need to look at the x and y. X is a function, and this is a composite function in which x is a function also of a t. That is, x is the function of one variable, and also y is another function of one variable. I have these functions explicitly, the f, g, and h, and I know that the f, g, and h, they are continuous functions. They are functions consisting of x, y, trigonometric. I know that these functions are differentiable functions on the domain. So I'm safe to use my chain rule. So if now let's look what's requested. It is requested to find dz by dt. But this is the required to find dz by dt. Let's write the chain rule, then apply to the function. The chain rule now, z is a function of two variables. If I expect to have two terms in my chain rule, so the first one is equal to a partial z partial x times the derivative of x with respect to t, dx by dt, and x is a function of one variable, plus partial z partial y times dy by dt. So now let's apply partial z partial x. Z is the function x squared y 3xy power 4. Now let's open the bracket for this derivative with respect to x. Fixing y, I'll end up with 2xy plus 3y power 4, okay, times dx by dt. X is the function sine to 2t. Derivative of x with respect to t is the function cosine 2t times the derivative of the argument 2 plus partial z partial y is the derivative with respect to y. Now I'll open my bracket. I have here x squared plus 3 times 4, which is 12xy cubed, right? Times the derivative of y with respect to t. Y is the function cosine t. If I have here negative sine t, I'm doing derivative with respect to t. Now I need to find values. I only find the derivative at the point or at the value t is equal to 0. يبقى بالتالي when I want to find this, خلاص I'm going to substitute in my x and find the value of x at 0. Okay, I don't need to resubstitute the expressions for x and y in terms of t and then substitute in the end. I could simply find the value of x at 0. I know x is the function sine 2t, and I have sine 0, which is a 0. خلاص يبقى x is a 0. And the y at the 0, y is the function cosine t. We have here cosine 0, which is a 1. Plus, I know the values. If I have t is a 0, x is a 0, and y is a 1, then dz by dt at t is equal to 0 actually is equal to, let's substitute y is x is b0 but this is a 0 يبقى هنا عندي كده 0 okay I have here 0 0 this term كله is turned out to be a 0 so I end up with 3 times 1 times 2 cosine a0 which is a 1 okay يبقى I have a 6 يبقى what is this? This is the derivative dz by dt of the composite function when I substitute it with t is equal to 0 okay. Now let's apply second example. I'm going to use the chain rule. I'm going to use the chain rule for finding dz by dt if z is a function of x, y, and x is a function of t, and y is a function of t. Okay, but definitely this is the same case. I'll do it directly. If it's a dz by dt, which is equal to partial z partial x times dx by dt plus partial z partial y times dy by dt. Okay, apply partial z partial x will be 2x. Okay, for dx, which would the derivative of tan, which is 6 squared, okay, plus partial z partial y by negative 2y, t derivative y بالنسبة ل t derivative is sec is sec a sector. Sec derivative of sec is a sector. Okay, that's it. And leave it as it is. Don't substitute. I don't need values. No, I do not. خلاص يبقى I now this case in which w is a function of x, y, this is a two variable function, and x is a function of two independent variables which are r and t. And I need to find partial w, partial r. So partial w, partial r. Now let's do a tree diagram. Maybe it will organize our thoughts. I know that w is a function of two variables. If I have two branches, one for the x and one for the y variables. Huh? Now x is a composite function of is a function of r and t, and y also is a function of r and t. But I have this tree diagram for my problem. If I want partial w, partial r with respect to r, I'm gonna arrive to this through two branches, right? Partial w, partial x, partial r, partial w, partial y, partial y, partial r. Let's write it down. يبقى بالتالي our rule will be partial w اهو partial w partial x times partial x partial r plus partial w partial y times partial y partial r. Okay, now let's apply to the functions. When I need partial w partial x, I will go down to the w function. يبقى apply the derivative. يبقى I'll have here 2xy cubed. Okay, x بالنسبة للr يبقى r يبقى t هنا is fixed, يبقى derivative is cosine t plus partial w partial y actually will be 3x squared y squared, partial y partial r here will be equal to sine t. That's it. Okay, got the idea? Now, this is another example. I have three variables for w. When I draw my tree diagram, I have the x, one for the x, one for the y, one for the z. Each one of x, y, z are function of r and s. I have from each one of these r and s. I could draw them combined, or I could draw them separately, but they remind myself that I have r existing in all these branches. So when I want myself partial w, partial here, it's requested to find partial w partial s. Where is s? S is these branches. Okay, بالتالي I have three terms in my function. I'll go partial wx, partial x partial s, wy ys وش كده wz zd zs. I have three branches. Okay, let's write it. بالتالي partial w partial s is equal to the w subscript x مش كده. Let's write it in these terms. xs wy في ys wz في z. Okay, but let's do the derivatives from the given function. wx actually is yz, xs is rs, wy is xz في ال E ال Y عبارة عن R over S. The derivative with respect to S is negative R over S squared plus WZ will be by XY times ZS. Z is the ln RS, يبقى derivative ln اللي هي 1 على RS في derivative البراكت with respect to S يعني R. Okay. Simplify and then leave it as it is. If I want values, then I add values, but at R equals 1 and S equals 1. If when R is equal to 1 and S is equal to 1, let's first of all find the values of X, Y, and Z at these points. Okay, then substitute. X here exponential يبقى I have e to the power 1. Y here R over S يعني 1 over 1. Z here ln 1 يبقى ln 1 is a 0. Okay, but now I have my values. It would be simple now to substitute. يبقى partial W partial S at these points is equal to Y is a 1, Z is a 0. يبقى the first term أي حاجة فيها Z بقى product يبقى turn out with a 0. يبقى دي 0. يبقى I'll end up with this one. R will cancel with this one. يبقى I'll end up with X, which is an E, and Y, which is a 1 over S, which is a 1. Okay, but my answer is the exponential term. Okay, value. Now the last concept here about implicit differentiation. برضو let's recall كده from functions of one variable. If I had a function capital F of X or Y is equal to 0, and I know that Y is a function of X. Okay, then we say now that Y is implicitly defined a Y. We say this Y is implicitly defined in the function. I don't have Y equal. I don't have as usual Y is equal to F of X. إنما I have Y defined implicitly in this capital function F. But if I have this case and I want to apply the chain rule, this is actually the final rule. Let's see how did we arrive at this. Say that I don't want, all I have is this capital function, and I need the derivative to find the derivative of the function y with respect to x. And I don't have y equal x to find f prime directly. I don't have this small f. I only have this capital F. So how am I going to apply? I'm going to apply to the capital function. خلاص يبقى بالتالي differentiate the function. Differentiate the function دي اللي هي f of x y with respect to x. يبقى I'm going to apply the chain rule. Now this is an application to the chain rule. Because I have f, a function of two variables, so I want the derivative. I'm going to say the derivative of f with respect to x times the derivative of x with respect to x itself, plus the derivative of f with respect to y times the derivative of y with respect to x is equal to 0. I have a 0 or constant on the other side. So now I have this the term that I need. This is the request. This is the required to find. So when I solve for dy by dx, I'm going to end up with dy by dx is equal to, take this on the other side, if I'll have minus partial f partial x على dx by dx. طبعا we must note here in the change of x with respect to x actually is a 1. And if it changed by 1, it will change by 1, it changed by 2, but this change actually is a unity always. So I'll end up with minus partial f partial x over partial f partial y. Okay, but this is another way to do implicit differentiation. You usually did it in this way, and you solve for dy by dx. But now you can do it directly and using this relation. Okay, you don't need to apply the rule. I don't know if you have an example. We can do examples about together. Right? Now, if I have this by implicit differentiation, if I have a function z, function of two variables, and it is implicitly defined in this equation f capital of x, y, z equals 0. And I do the same, and if I have this, and I want to apply the chain rule, and I know that z is a function of x or y, don't forget, okay? then I need to solve, say, مثلا, I need to find the derivative of z with respect to x. I don't have the small f to do the job. I only have this capital F. If I'm going to apply the chain rule, but to the capital F function B. فبالتالي I'll have partial F partial, I'm doing it with respect to all the variables here, صح؟ يبقى x في derivative of x with respect to x, right? نفس same as before. Also I have still y, يبقى بالتالي I'll have the term with the y, يبقى في derivative ال y with respect to x plus the partial f partial z في derivative ال the partial z partial partial z partial x, okay, is equal to 0. Now I have the same, x is the independent variable, so then this is a unity, so y is independent variable, so it does not depend on x definitely. So بالتالي this term always will be 0. There is no change in y if x changes. And this is the term that is required to find. This is the term that I want to find. So بالتالي I'll do the job and I'll end up with solving for partial z partial x. I will have partial z partial x is equal to minus partial f partial x, okay, over partial f partial z. Okay, but this is the rule. But it's a simple rule. If you have a function defined implicitly, all you need to do is get the partial derivative of the capital F function with respect to the variable x, with then over the derivative with respect to the variable z. Similarly, I could find a similar formula for the y, a partial z partial y. This time I have in the numerator partial f partial y, similarity over partial f partial z. Okay. If it's defined implicitly, you could either go like this, but this is the long way, or you could go using this rule, which is the direct way. Okay. Definitely we need to do direct ways. Let's do this example. If I need to find partial z partial x, if z is equal to f of x y, and it is implicitly defined in this function. So first of all, I need to clarify what functions I'm dealing with. What is my capital F function? But I should combine all the terms on one side, but this is x, y, z minus ln x plus y plus z, okay? Now I need, this is equal to 0 because I went there, I went to the other side, I ended up with a 0 on the right hand side. But now I have my function capital F. Otherwise, I'm going to apply the rule for the implicit differentiation. I need partial z partial x. Okay, I declare that I know from my rule that partial z partial x is minus fx of f sub x over fa sub z in a partial f partial z. As I do the job on this capital function, I have this negative sign. What is the derivative of this function with respect to x? يبقى x, y, z with respect to x, I have a y, z minus derivative then is 1 over x plus y plus z times derivative in bracket with respect to x, which is also a 1. Okay, خلاص, this is partial f partial x over the derivative with respect to z. Z is here. يبقى بالتالي I'll have xy. Now I'm treating z as if it's one of the independent variables when I'm doing partial f partial z. Okay, and I'll have y1 over x plus y plus z. Okay, that's it. This is my final answer simply without doing the job on the original equation. I did it on the function capital F that I constructed and then applied the rule of implicit differentiation. Last example, this is a simple one. X cubed y cubed 6xy, and I want y prime. Why y prime? لأنه y is a function of x only. So واضح إنه y, and I notice y is implicitly y is implicitly defined in this function. So my function f of a function of x or y is the function x cubed plus y cubed minus 6xy equals 0. I prepared my function. Now from the rule of the implicit differentiation, I know that y prime of dy by dx actually will be minus f x over f capital F with respect to x, I left f capital y. يبقى عندي هنا negative. What is partial f partial x؟ يبقى 3x squared minus 6y. What is f with respect to y? 3y squared minus 6x. That's it. But this is my final answer of the partial derivatives of using implicit differentiation. Okay, thank you.